All right, so we've described the system with these properties. Now, these properties come in two flavors. You have extensive properties and intensive properties. The extensive properties are the ones that scale with the size of the system. If you double the system, they double in their numerical number. For instance, the volume. If you double the volume, you double. V doubles, right? I mean, that's obvious. The mass. If you double the amount of stuff, the mass will double. Intensive properties don't care about the scale of your system. If you double everything in the system, the temperature is not going to change. It's not going to double. Temperature stays the same. So temperature is intensive. And you can make intensive properties out of the extensive properties by dividing by the number of moles in the system. So I can make a quantity that I'll call V bar, which is the molar volume, the volume of 1 mole of a component in my system. And that becomes an intensive quantity, a volume which is an intensive volume. Okay? The volumes per mole of that stuff. Okay. So as I mentioned, thermodynamics is the science of equilibrium systems. And so it also describes the evolution of one equilibrium to another equilibrium. How do you go from one to the other? And so the set of properties that describes the system in equilibrium doesn't change. Okay? So these unchanging properties that describe the state of the equilibrium state of the system are called state variables. Okay. So the state variables describe the equilibrium state. And they don't care about how the state got to where it is. They don't care about the history of the state. They just know that if you have water at 0 degrees Celsius with ice in it, that you can define it as a heterogeneous system with a certain density for the water, a certain density for the ice, et cetera, et cetera. Okay? Doesn't care how you got there. We're going to find other properties that do care about the history of the system, like work that you put in a system, or heat that you put in a system, or some other variables. But you can't use those to define the equilibrium state. You can only use the state variables, independent of history. And it turns out that for a one-component system, one component meaning one kind of molecule in the system, all that you need to know to describe the system is the number of moles for a one-component system. And to describe one phase in that system, one-component homogeneous system, you need n and two variables. For instance, the pressure and the temperature, okay? Or the volume and the pressure. If you have the number of moles and two intensive variables, then you know everything there is to know about the system, about the equilibrium state of that system. There are hundreds of quantities that you can calculate and measure that are interesting and important properties, and all you need is just a few variables to get everything out. And that's really the power of thermodynamics, is that it takes so little information to get so much information out, so little data to get a lot of predictive information out.